So this lecture is Springs and Conservation of Energy. It's section 4.7 from your textbook. And this will close off the energy portion of the energy and momentum unit. So we learned about the law of conservation of energy. It's that the energy is conserved throughout any sort of interaction, as long as we account for all types of energy. Now, this law makes a lot of physics problems a bit easier to solve because of the fact that work and energy are scalar quantities. We don't need to draw vector diagrams. We don't need to calculate angles. We can end up determining things with these absolute magnitudes of work and energy, and we can use those to find out what our speed might be or our height might be after a certain interaction. So when we have motion that is occurring in a single plane, it's often a lot easier to do these. When we have motion that is that's vertical, we have gravitational potential energy to add. But when we're only in the horizontal plane, we don't have to account for gravitational potential energy. Now this whole lecture is going to be about springs and conservation of energy. So here's a problem that's a horizontal situation. So we don't have a gravitational potential energy, but we have a cart that is traveling and it hits a spring. So basically we're ignoring friction in this question. And we're going to see how to solve this. So the first thing to note is that the energy before has to equal the energy after. So our energy before is entirely kinetic energy. So this would look something like this. Here's our energy before. It is all kinetic, so it's 1/2 mv squared. Our energy after is that spring energy. It's 1/2 k delta x squared. Now we're asked to solve for our v. How fast was it traveling before? So rearranging this equation for v, the 1/2 can be divided on both sides to be taken away. We have k over m delta x squared. Our k value is 155. Our m, let's click back on here, is 0.25. And our delta x is 0.06 because it's in centimeters. We have to write it that way. So this can then be calculated as 155 divided by 0.25 times 0.06 squared. Gets us to 2.23. Sorry, with the square root of this. And then we would find the square root of that. And we could write for the significant digits, which, going back to the question, it would be limited to 2. So that's 1.5 meters per second. So this problem, we have a 70 kilogram person. They step through a window of a burning building. They drop to a rescue net that's held 8 meters below. And the surface of the net is 1.40 meters above ground. And you're asked, what must be the value of the spring constant for the net so that the person just touches the ground when the net stretches downward? So this is a problem that involves gravitational potential energy and spring energy. And here's what the situation looks like. We have a person, they're 70 kilograms. There's a distance between them and the top of the net, which is 8 meters. The net stretches down, and it stretches down 1.4 meters. So this is our entire situation. Our energy before equals our energy after, which is totally So our energy before is totally gravitational potential energy. Our energy after is all spring energy. So this becomes mgh equals 1/2 k delta x squared. So we'll need to rearrange this for solving for k. That gets us to k equals 2 mgh over delta x squared. Now, when you look at the question, it gives us 3 significant digits for each value. So we have 70.0 kilograms, 8.00 meters, 1.40 meters. That means when we're using our values here and we're substituting in, we have to use 3 significant digits. And for our gravitational acceleration, we should extend it to 3 as well. So I'm going to write 9.81 instead of just 9.8. Now this height is actually, I was about ready to write 8.00. It's actually 9.4. 9.4 because it's the 8 plus the additional 1.4. This whole thing divided by 1.4 squared, because that's our extension. And when I put this in the calculator, you'll see I get 2 times 70 times 9.81 times 9.4 divided by 1.4 squared. I get k equals 6.7, which I'm going around to 6590 newtons per meter. I know the slideshow has a different answer there. They're off by 10. That's because they didn't use the 9.81. Another problem here, we have a block that's dropped on a vertical spring. We know the spring constant. The block compresses the spring by 15 before it stops and starts to return. So determine the height from which the block was dropped. So going back to here, oops, that's another question. So we have again, these questions, anytime we have conservation of energy, we have energy before equals energy after. And in this problem, we have a block that is we have our gravitational potential energy is our energy before, our spring is the energy after. We have 1/2 of k delta x squared, and we have mgh here. We have to solve for h. So this is going to be essentially k over 2 mg delta x squared. And I have 2 significant digits for these values. So my k is 180. My m is 0.2. My g, I'm going to put 9.8. And my extension is 15 centimeters, 0.15 squared. So that works out to 180 times 0.15 squared divided by 2 divided by 0.1, or 0.2 rather, divided by 9.8. So I end up with a height of 1.033. So that's my height, but I have to subtract that 15 to find out the height from which it was dropped, because that's that also accounts for the spring's compression. So I have to take my answer here, which is 1.033, and I have to subtract from that. So my delta H, 1.033 minus the 0.15, and let's do it over here, minus 0.15, oops, gets me to a height of 0.88 meters. So we dealt with questions that were in one dimension, either horizontally or vertically. Now let's look at a problem that's in two dimensions. So we'll have a horizontal and vertical component to this. These get a bit trickier to do, and this is where conservation of energy outshines using your uniform acceleration equations, your equations of motion, because we can actually determine, we can solve problems like this without having to use, without having to break our value or our givens up into components. Let me show you how this works. So we have, I'll read the question. It says there's a block with a mass of 2.0 kilograms. It's held against a spring. The spring constant is 250 newtons per meter. The spring is compressed 22 centimeters, and then the block gets released. So this gives the block a kinetic energy, and it travels along this frictionless surface and goes up a frictionless ramp. Now it's going to ask this in parts. I'll just read them all first. So it says determine the elastic potential energy stored in the spring before the mass is released. Calculate the speed of the block as it travels along the horizontal surface. So what we're going to do is we're going to look at this problem in the sense that I guess that we could answer each of the individual parts. So let's figure out our ET before is equal to our ES, and our ES is 1/2 of K delta X squared. So that is 1/2 of 250. Delta X was, I think, 22 centimeters. Yeah, 0.22 squared. So 250 times 0.22 times 0.22 is 12.1 times 1/2, sorry. I get 6.05 or 6.1 joules. Now, that was my first part that asked me about the energy before. The second part says calculate the speed of the block as it travels along the horizontal surface. So here, if this is our energy, then our kinetic energy, that's our potential energy, our kinetic energy has to equal that potential energy. So that's 1/2 of m v squared. So this must be 6.05 because I have to use the exact value of 1/2, and my mass was, let me just go back here, it's 2 kilograms. So this becomes, V is going to equal 2 times 6.05 over 2, and I have to find the square root of that. So it's going to be the square root of 6.05, which is 2.4, 2.46, because I have to round, but actually I have to round again for significant digits, 2.5. So my first solution here, my energy before is 6.1. Using that energy, I can find out my velocity, which is 2.5 meters per second. Going back to the question here, it says now determine how far along the ramp the block will travel before it stops. So this gets interesting now. So what we have to do is we have to find out how we can find out our height from this. Now, if we had a potential energy of this before, and that turned into kinetic energy, that's now going to turn into gravitational potential energy as it slides up the ramp. So my ET equals ET after, right? This was equal to my ES, which has to be equal to my EG. So I have 6.05 has to equal mgh. And my h is 6.05 divided by 2 divided by 9.8. So 6.05, let's go back here. 6.05 divided by 2 divided by 9.8 gets me to 0.3086 as my height. I'll just round it like that. But this is my height that I travel up the ramp. So if I'm looking at the ramp like this, at this height, my block will hit here. But what I was asked to find out was how far up the ramp does it travel. So this is my distance that I have to figure out here. So I really have a right angle triangle where I know this angle because that was given. I know this height because I had to calculate it. I need to find that d, that it traveled up. So using trigonometry, I know that sine of 30, or rather d, is equal to that h value times sine of 30 degrees. Sorry, other way around. Let me redo this. Sine 30 degrees equals 0.3087 over d. So d equals 0.3087 over sine of 30 degrees. Sine of 30 degrees is going to be 1/2. I'll just type it in here. When I divide, that means it's going to double it. So my distance is 0.62 after I round, and that solves that problem. So let's continue on with this lecture. There's just a little bit left. We talked a bit about this earlier, but there are types of forces that we refer to as conservative and non-conservative forces. So the forces that we were dealing with were referred to as conservative forces. So that means the amount of work they do on a moving object does not depend on the path of the object. So this is an example here. If we have a boulder and it's on top of a mountain, one side of the mountain has a very steep hill, the other side is a more gradual hill. If we don't consider friction, the boulder will hit the ground at the same kinetic energy whether it goes off on the left or the right. But friction is a non-conservative force. So the amount of work done by non-conservative force depends on the path taken by the force. So when you consider friction, if you are traveling a longer distance and you're experiencing friction, there will be the amount of work will be different because the force that you were experiencing you were experiencing that force for a longer time because you were traveling a longer distance. The example for this one is skiers going down a hill. Now, if a skier goes straight down a hill, they will be traveling at a faster velocity than a skier who's kind of following an S shape around the hill, because every time that skier makes a turn, the skier in red in this case, they are losing some of their energy to the non-conservative force of friction. So when you deal with non-conservative forces, the law of conservation of energy still applies, but there's lots of energy exchanged between the moving object and its environment. So that makes questions a bit more difficult to solve. So this last question involves non-conservative forces, and the non-conservative force here is thermal energy. So what we're going to see here is we have a roller coaster, and our values are given on the image. they ask us to put it in 3 significant digits, even though I think there's 2 significant digits. For one of those is limited. 6.0 would be 2 significant digits, but since we're asked to put it in 3 significant digits, we'll solve it in 3 significant digits. But what's important here is that we have to consider that our thermal energy is also going to be part of our conservation of energy equation. So you see our ETA. So situation A is when we're at the point at 15, that's 15 meters above. We're traveling at 4 meters per second squared. Or sorry, we're traveling at just 4 meters per second. ETB, we're at 6 meters, but we don't know the velocity. So our kinetic energy at A plus our gravitational potential energy at A has to be equal to the kinetic energy at B plus the gravitational potential energy at B plus that thermal energy loss. So in order to solve this, I'm going to start with that where it says EKA plus EG A equals EKB plus EGB plus E thermal. And we're going to rearrange that to solve for EKB. EKB is equal to EKA, the situation at A, for kinetic energy and gravitational potential energy, minus EGB minus E, and I'll call it T for thermal energy. And this is 1/2 mVB squared. This is 1/2 mVA squared. This is mGHA. This is 1/2, or sorry, this is mGHB. And this is our ET for the thermal energy. So now we're going to multiply everything by 2, divide by m in each of these cases here, and then we'll square root everything. So multiply this term by 2m, we're left with just a VA squared. Multiply this by 2 over m, and we end up with 2GHA. Multiply this by 2 over m, we end up with 2GHB. And then the ET term, we're going to have 2 over m ET for that thermal energy. So VB now would equal, let's substitute these values in. We're traveling at 4 meters per second in the initial case at point A. 9.8, we're going to put 9.81 because we're asked to solve this in 3 significant digits, so we'll add the 3 significant digit value for G. HA, the height is 15 for at point A, minus 2 times 9.81 times HB, which is 6, minus 2 over 200, and this is 3,400. So entering this into our calculator, we end up with, let's see here, we have, I'll put brackets to start, then we have 4 squared plus 2 times 9.81 times 15 minus 2 times 9.81 times 6 minus 2 divided by 200 times 3,400. And I need to find the square root of this. I end up with a VB of 12.6 meters per second.